Ajahn, your mic is muted. I think we cannot hear you.
Sorry, I mute my microphone. We everyone in this room can hear my voice,
Yeah, Ajahn,
but you
now.
cannot hear.
Yeah, now we can hear.
Uh, we have to solve this problem because yeah, people in the room hear echo. I turn that speaker off, so people in the room, you can hear my voice, right? Okay. How about the Zoom? People in the Zoom, you can hear my voice?
Yeah, Ajahn, now we can hear.
Okay, good. Okay, so back to the beginning of this problem. Okay, I try to keep it well briefly. For refinery optimization, we have the input for these systems. Let me explain you from this graphic. Okay, we have for process distillation, we have reformer, and we have cracker, right? And finally, blending. So, for distillation, we receive C1, C2, which is a different types of crude oil. Okay, let's say we have two possible available crude oil. Okay, C1 and C2, and for distillation column, it splits crude oil to light naphtha, medium naphtha, heavy naphtha, light oil, heavy oil, and residue. Okay. Well, the yield for each type of crude C1, C2. Come on, it's quite slow. Okay. The yields are shown here in this table. Okay. So if you send 1 barrel of C1 to distillation, you obtain 0.1 light naphtha, 0.1 barrel of light naphtha, zero 0.2 barrels of medium naphtha, 0.2 barrels of heavy naphtha, and well, 0.12 of light oil, 0.2 heavy oil, and 0.13 of residue. Okay. What else? So now for naphtha, we can send naphtha to reformer. And for reformer, we have a yield. Okay, here, information regarding the yield here. Okay, reform from reformer, we obtain reform gasoline. Okay, no matter you send light naphtha, medium naphtha, heavy naphtha, it's changed to reform gasoline, the same thing, the same product. Okay, but of course, you send different inputs, the yields are different. Okay, and well, the octane number of reform gasoline is much higher than light naphtha, medium naphtha, and heavy naphtha. And well, we also have cracker. Okay, for cracking process, it receives oils, right? Light oil, light oil, and heavy oil. Okay, and well, the products from cracking consist of crack oil and cracked gasoline. Cracked gasoline has octane number of 105. Okay. Okay. For crack oil, what we're going to do with crack oil? Crack oil is used for blending fuel oil and jet fuel. Okay. But for cracked gasoline, you mix cracked gasoline with reformed gasoline and light naphtha, medium naphtha, and heavy naphtha. Okay, to form petrol products. And what else from distillation column? We had residue. For residue can be used for producing lube oil or blend with light oil, heavy oil, and crack oil to form jet fuel and fuel oil. Okay, and if you decide to produce lube oil, 1 barrel of residue form 0.5 barrels of lube oil. Okay. Okay, now we move to the last process, which is a blending process. For blending process, we have petrol. We have two sorts of petrol. We have regular and premium one. The stipulation concerning the regular petrol, it's the octane number. The octane number for regular petrol must be greater than 84. Okay, must be at least 84. And for premium, the octane number should be at least 94. Okay. Okay, and for petrol, in order to blend the petrol, you can blend light naphtha, medium naphtha, heavy naphtha, cracked gasoline, and reformed gasoline. Okay. Okay, now we move to the next product. It's jet fuel. For jet fuel, the stipulation concerning this product is vapor pressure. Okay, the vapor pressure must not exceed 1 kilogram per square centimeter. Okay, and the vapor pressure for light, heavy, and crack oil and residues are 1.5, 0.6, 1.5, and 0.05 kilogram per square centimeter. Okay, and what about fuel oil? For fuel oil, you must blend light oil, crack oil, heavy oil, and residue by using a certain ratio. The ratio is 10 to 4 to 3 to 1. Okay. So you see that for jet fuel and fuel oil, you blend light oil, heavy oil, crack oil, and residue together. Okay. With different formula. And their availability and capacity limitation. Okay. The availability of crude 1 is 20,000. For crude 2, the availability is 30,000. Okay. And at most, the capacity of distillation process is 45,000 barrels per day. And the capacity of reformer is 10,000 barrels. For cracker, the capacity is 8,000 barrels. Okay. And the daily production of lube oil must be between 500 to 1,000 barrels. Okay. And the next condition is premium motor fuel production must be at least 40% of regular motor fuel production. Okay. And the profit contribution from the sale of final products are 700. For regular petrol, it's 600. Jet fuel is 400. Fuel oil is 350, and lube oil is 150. Okay. The question is, how should the operations of the refinery be planned in order to maximize total profit? Okay. What we want from this problem? We want to maximize the profit, right? Okay. And in order to maximize the profit, we have to make decision on the amount of crude 1, crude 2, and what else? The amount of each stream. Let's say we have crude 1, crude 2, right? And we get light naphtha, medium naphtha, heavy naphtha, light oil, heavy oil, and residuum. So for light naphtha can go through, well, reformer, or it can be sent to blend regular petrol directly, or directly sent to blend to form the premium petrol. Okay. The same for medium naphtha, right? It can be used to blend regular petrol, premium petrol, or it can be sent to reformer. Okay. Also the same apply to heavy naphtha. Okay. So you see that if you look at the reformer receive this stream, the amount of light naphtha that's, well, we receive. Medium naphtha we receive for this process, heavy naphtha we receive for this process. Okay. And the output is reformed gasoline. And from reformed gasoline, the reformed gasoline can be used for blending the regular petrol or premium petrol. Okay. Now we move to light oil. Light oil, well, we can send light oil to cracker, or it can be, well, sent to blend jet fuel or fuel oil. Okay. Heavy oil also the same. Okay. And if you look at the cracker receive light oil and heavy oil. Okay. And we have two products, cracked gasoline and cracked oil. Okay, now look at cracked gasoline. Cracked gasoline, well, can be split into two ways. One part we send to regular petrol. The other part we send to blend to form the premium petrol. Okay. Crack oil also the same, right? Crack oil, well, we send to blend jet fuel and fuel oil. Okay. The last component, residuum. Residuum can be used for blending the jet fuel or fuel oil. Okay. And the rest we use it to form the lube oil. Okay. Now we look at the blending process. For blending process, this process receive light naphtha, medium naphtha, heavy naphtha, regular, reformed gasoline and cracked gasoline, okay, in order to form regular petrol. And if we look at the premium petrol is blended from light naphtha, medium naphtha, heavy naphtha, reformed gasoline, and cracked gasoline. Okay. Now, well, for jet fuel is blended from light oil, heavy oil, crack oil, and residue. And for fuel oil, well, it's blended from light oil, heavy oil, crack oil, and residue also. Okay. The same pattern, but different variable. You see that different variable. Okay. And for lube oil is produced from residue. Okay. So for the objective function, we want to maximize profit, right? We have no information regarding cost. Okay. So we don't have to consider the cost. We can treat that the costs are almost the same, right? The cost does a change by changing the decision variable. And the profit is, well, it's contributed by the profit from premium petrol, regular petrol, jet fuel, fuel oil, and lube oil. Okay. So what about the decent variables? The decent variables are all variables we show here. Okay. In each stream. And you see that, well, can we eliminate this variable like light naphtha, medium naphtha, heavy naphtha, light oil, heavy oil, and residue? Yes, we can get rid of all these variables, right? Because you know that for light naphtha, it's always, well, it's a function of C1, C2 because you have information regarding the yield, right? Yes. But if you get it, if you, well, remove all these variables, of course, you can write the function of this. But you see that the problem is it render the problem to be more complex because you see that light naphtha will be split into 3 streams, right? And instead of, while writing this stream as light naphtha one variable, you going to, by eliminating this variable, you're going to write it as a function. So it becomes more complex. Okay. So keep all these variables with as our decent variables. Okay. And because we keep all these variables as our decent variable, we need the constraint, this constraint. Okay. We write that relationship as equality constraint. Okay. Like naphtha equals 0.1 C1 plus 0.15 C2. Okay. This information from the yield. Okay. The first table regarding the yield. Okay. So, well, medium naphtha, heavy naphtha also, well, you get information from the yield. Okay. So for light oil, heavy oil, and also residue, also the same. The same apply here. The same rule, same pattern. And we have capacity of the distillation. No, yeah, distillation column. The distillation column is limited by 45,000, right? So C1 plus C2 must be lesser or equal 45,000. Okay, and C1 must be less than 20,000. C2 must be less than 30,000. Okay. Okay, and now we move to the next constraint. How do we get this constraint? Light naphtha equals, well, light naphtha that we send to reformer, light naphtha we send to regular petrol and premium petrol. We get this this constraint, okay, from mass balance, right? Because once at this point, oh, it's raining outside. Light naphtha equals L into RG, right? Plus L into RP, L into PP, okay? Because only three possible destination for light naphtha you produce, okay? So we formulate light naphtha, medium naphtha, and heavy naphtha this way, okay? And the next one is reform gasoline, okay? Reform gasoline. This one, how do we get this equation? From yield, right? Yield of reformer, okay? Because once we send 1 barrel of light naphtha to reformer, we get 0.6 barrel of reformed gasoline, right? Okay. Okay. What about this? This one is the limit of the capacity of the reformer, right? The reformer, the capacity of reformer is 10,000. Okay. And what about this? This is a mass balance of reformed gasoline because, well, reformed gasoline produced must be sent either blending the regular petrol or blending the premium petrol. Okay, the first two constraints in this slide are from the mass balance, okay? And the next one, this one, Cg equal 0.28 LO2C plus 0.2 HO2C. These are yields, right, of the cracked gasoline and crack oil from cracker. Then we move to the next one, cracked gasoline. This is a, what is it? This one, mass balance, right? This one also mass balance, okay? And this one, this one is the capacity of cracker, okay? The next one is the mass balance, right, for residue. Okay. Now we move to the mass balance of the regular petrol, premium petrol. This is mass balance at blending, okay? This is mass balance for jet fuel, blending the jet fuel and fuel oil, okay? And this one, what about this one? This one is yield of the lube oil, okay? Okay. What about this? This constraint. $90, $80, $70, $115, $105 octane number of regular petrol, okay? So it's linear blending, okay? Linear combination. Okay, normally you multiply the amount and octane number of each component, okay? Sum up and divided by the total amount of regular petrol. However, if you write that way, I mean, you divide these terms with RP, it renders this inequality to nonlinear function, right? So to linearize it, one way, we multiply both sides by RP, right? Okay. So you get this equation, no, inequalities. And this inequality, this expression is linear function, right? Okay. This one also, the linear function now. And the next one, it's vapor pressure. For this one, of course, you have to divide it by JF, or jet field, the amount of jet field. But again, to make it linear function, we multiply both sides by JF. Okay. We know that JF cannot be negative, cannot be zero. Okay. Always positive. This one also, right? RP and PP cannot be zero. Okay. And these three constraints we formulated from the ratio for blending the fuel. Okay. 10 to 4 to 3 to 1. Okay. Of residuum. And the limit of production of lube oil must be produced at least 500 and must be less than 1,000, right? And the last one, premium petrol must be greater than or equal zero point 0.4 of RP, regular petrol. And the most important constraints, this one, all variable must be greater than zero, okay? Must be zero or positive. Okay, so you can solve this problem by using Excel. I will show you. I have completed this sheet yesterday, so well, I put all the what's it decision variable here. You see C1, C2, LN, MN, HN, LO, HO1. Okay. The cell to store the uh decision variables are here in this B column. Okay. Then we formulate the objective function. Objective function is here. Objective function is calculated from this, you see, RPPP, JF, FO, and L, right? Okay. And then each constraint I show in the slide here, okay, formulated here. And you see that always, well, I keep the right-hand side to be a constant. For, well, the first constraint, we have this one. You see Ln equal 0.1 C1 plus 0.15 C2. Okay. To keep the right-hand side to be zero, very simple. You can write Ln minus 0.1 C1 minus 0.15 C2 equals 0. Okay. And it is here, you see. Okay, we have ln subtract by 0.1 C1, 0.15 C2. Okay. Okay. Hmm? Maybe any questions? Okay, any questions? You want to see? Do you want to see any formulation of any constraint?
Yeah, John, the objective function.
Objective function is here.
Yeah, how did we make from?
Yeah, just 700, right? Time with multiply with B38, B38 is PP, okay? And 600 of RP plus 400 of JF, 350 of FO plus 150 of Luboy. Okay? So anything else?
John, can you slide down a little?
Okay, one moment. Which constraint you want to see?
Yeah, from 17 below to
17
the,
here?
yeah, from 17 to the end below.
Okay.
Yeah, like this. Okay.
Okay. So you formulate it and then well you use solver to solve. And you see that I already solved this problem, you see. And some of the cell, it's you see that it's heavy oil to fuel oil. You see that it's 2.37. Yeah, with time with 10 power by power to minus 13. This one is close to zero. It should be zero. Okay. This one also, well, it cannot be negative. It's zero, actually. I know you cannot hear anything because I did not speak. Okay. Okay, so you can do it by yourself. Hmm? This one. If yes, then we move to next problem. Which part? Which cell? Pardon? L G? Huh? L? What? Which cell? H? Yeah. What do you want to see? Yeah. Okay, so well, you can finish it later. Okay. Let us move to
Yeah, Ajahn, can you
yes.
please scroll from the first one to the last so that we can just take pictures to check the answer later from the first one, from number one to the last. Yeah, and also this and the again, please, Ajahn, again. Yeah.
Hmm. Okay. So okay, so the next problem is factory planning. Well, you can get from the title factory planning. It should be multi-period optimization problem. Okay, so well, we have a factory which makes 7 products. Okay, by using different machines for different. No, how many of it? One, two, three, 4, 5 types of machine. Okay, and this factory has 4 grinders, 2 vertical drills, 3 horizontal drills, 1 borer, and 1 planer. And well, in order to produce each product, it requires well different hour of each machine. Okay, so for example, in order to produce product 1, you need 0.5 hour of grinder. Okay, zero point 0.1 hour of vertical drill, zero point 0.2 hour of horizontal drill, and 0.05 hour of borer. Okay, and the first, yeah, this contribution This row, it's contribution to profit. Okay. So you see that product one contributes to 10 well dollar yeah 1 unit, 10 unit of profit. Okay. And product two contribute to 6 units. Well, you can see from this table. Okay. So we plan for 6 months. Okay. From January to June. Okay. And we also have plan for maintenance of the machine. For example, in January, one grinder will be in maintenance. Okay. So totally we have 4 grinders, right? So that means in January, we have only 3 grinders available. Okay. And in February, we plan to shut down 2 drills, horizontal drills. Okay. In April, 1 vertical drill will be offline. Okay. And you see May and June also. And what else do we have? Marketing limitation. This table show the marketing limitation for each product and each month. The next thing is we can produce each product and we keep it in the storage. Okay. And the storage capacity is 100 unit. Okay. And there is a cost to store the product. Okay. 0.5 per unit per month. Okay. And in the first month, there are no stock. Okay. But it is decided to have a stock of each type of product, 50 units at the end of the June. Okay. And the factory works 6 days a week with 2 shifts. Okay. 8 hours each day. Okay. So one day, the factory operates 16 hours. Okay. Okay. When and what should the factory make in order to maximize the total profit? So the objective is to maximize the profit, right? There are 2 ways to formulate this problem. Okay. First, if we have a contract regarding the sale, the amount of sale, you see that we have information regarding the marketing limitation, right? If we have contract on that, that means, well, we have to sell the product, each product, each month. We have to follow this table, this amount. Okay. So in that case, our revenue become constant, right? Because the revenue follow that table. Okay. So in order to maximize the profit, we have to minimize the cost instead. Okay, the same thing, right? So what about the cost? In this case, cost is the function of what? Of storage, right? Because you can produce the product in advance and then you keep in storage, right? But you have to pay for storage costs. Okay. What about our decision variables? We have decision variables on, well, the production. What product? Okay, product A, and which month? Okay. How many product A to produce in J month? Okay, so we have a matrix of Pij. Okay, I standing for product and J standing for month. Okay, we have a matrix of that. The matrix P with 42, right? 42 elements, which is a production. And we have storage. Okay, storage, the amount of product at the beginning of each month. Okay, from January to June. What else do we have? We have Sij. Sij is the amount of product we sell each month. Okay, each product each month. So you see that each month, for example, we start from the first month, the PI1, okay, product I, first month, PI1 plus TI1. TI1 is the amount of product I, right, in the beginning of the first month, equal the amount of product I you sell in first month, okay, plus the remaining. What is the remaining? The amount of product I, right, in the storage at the beginning of the second month. Okay, you follow this pattern until the last month, the 6th month. At the beginning of the 6th month, well, what you produce plus what in the stock at the beginning of that month equal what you sell in that month plus 50. Why plus 50? Because the factory designed to fill the stock with 50 units of each product, right? So it should be 50 at the end. Okay. And these the amount of sale. Okay. Because we say that, well, we have a contract, right? So you have to fulfill that table, the marketing limitation table. Okay. So we know each element of this. Okay. And at the beginning of the first month, each product must be 0, right? Because there are no stock in the first month. Okay. And each month, you cannot store more than 100. Okay. Okay. And well, Tij must be greater than or equal 0. And Pij also must be greater than or equal 0. Okay. Okay, now we move to the next constraint. It's a constraint on grinding. For grinding, on the left-hand side is the amount of time, right? The time in a unit of hour required to produce product 1 to 7, okay? And on the right-hand side is the amount of, well, the available machine time, okay? The grinder time. Because the first one is shut down, right? One grinder is offline. So you can use only 3 grinder in January, okay? This one, 3, it's a number of machine, number of grinder. What about 4? This 4 is standing for what? 4 week, right? In 1 month. And this 6 days a week. And 2 shifts a day. And 8 hours per shift. Okay. The next constraint is vertical drilling. Okay. And horizontal drilling. And boring planning. Okay. And now we look at the objective function. In this case, we minimize the cost, right? Maximize profit equals minimize the cost. And the cost is 0.5 time with what you store in each month. Okay. Okay. So then you can formulate the problem, this objective function, and all those constraints. Okay. Alternatively, if we treat the limitation on the market as the maximum product that we can sell. It's not a contract. That means, we don't have to fulfill that contract, but we maximize the profit. Why we consider those limitations as the maximum that we can sell. Okay, we cannot sell more than that. Okay, in this case, of course, with our contract, right? Okay, with our contract, we maximize the profit. Okay, and it can be what is the profit in this case? Is not minimize cost anymore. It should not be minimize the cost. Oops, sorry. Sorry, this one should be maximize profit. Okay. Maximize the profit. So we have to write the profit as a function of these variables, right? So we know the contribution of each product, right? Sum up all each month. Okay. And then we subtract by the storage cost. Okay. Now we look at this variable. We use the same set of these variables. Okay. Constraints are quite similar. Oh, but this is not correct. Sorry. This should be inequality. Sorry. These constraint should be inequality constraint. The cell must be lesser than or equal 500. Okay. Each one should be inequality, not equality constraint. Sorry about that. Okay. Yeah, let me correct it. Just one moment. Okay. So it should be lesser or equal. Okay. Like this. And in the first month, there's no stock, right? The same. And well, the maximum storage is 100. And all P and S must be greater or equal 0. Okay. It cannot be negative. We call it non-negative condition. Then we have a set of constraints from grinding, vertical drilling, horizontal drilling, boring, and planning. Okay, the same. Okay, so any questions regarding this problem? Hmm? Hmm? Well, what? Which? Hmm? Just remember, this is the demand, right? Is the second product, product two. So what is your question? I think this include all, wow, each month, right? All months. Hmm? Right. So the product two should be 6. Why I put 8 there? Oh, 8 and 4. Okay, it should be 9, 3, yeah. 9, 3, 11, 4, 8. Disappear. Why? Ah, yes. Let me correct this. 6, right? 6, and this one should be 6, right? 6. And what about the next one? Next one is 8. 8 and 4. Okay. Okay, so one moment. This one should be like this. Should be 6 of S2, right? And 8 of S3. And this one was missing previously, S4. Mhm. Okay, any questions? I give you homework, okay? Why? Your internet connection is unstable. My internet connection, okay, good. Yeah, there are two possible way to formulate the problem. The first one without contract, with contract, and the second one without contract, right? So you check again about the problem we formulate, and then you solve each case by using Excel. It's okay. Okay, you do it by yourself. I will open the assignment in my course view. Okay, and then while you finish that and submit your assignment through my course view. Okay. Okay, so now we move to the next one. This curve fitting. For curve fitting, well, let's say we have this data. X is our input and Y is our output. Okay, input, output. And of course, we change input. We we obtain different output, right? And we see the trend. Okay. So the question is, first, we're going to formulate the optimization problem in order to fit the best straight line in the form of y equal bx plus a, where b and a are constants. Okay. To, well, for the data given, and the objective is to minimize the sum of absolute deviations, okay, of each observed value of y from the value predicted by the linear relationship. Okay, we're going to fit those data to this straight line in order to reduce the sum of absolute deviations. Okay, and the second one is we want to fit the best straight line like this, y bx plus a, where the objective is to minimize the maximum deviation of all the observed values of y from the value predicted by linear relationship. Okay, you see that once we predict the straight line, well, we have deviation, right? We try to minimize the maximum deviation, okay, in the second case. And the third one is we want to fit the best quadratic curve in this form. Okay, we have three parameters, three constants, okay, using the same objective as in 1 and 2, okay. So for this curve fitting, for the first one, it's quite straightforward. We minimize this function, summation of the absolute deviation, yi subtract by summation of bxi plus a, okay? Okay, and we have to take the absolute because that, well, all the deviation must be positive, okay? And we collect all deviation, positive deviation, okay, by summing it, okay? Then we find a and b, which a and b that can, well, obtain the minimum sum of deviation, positive deviation, okay. And for the second case, where we want to minimize the maximum deviation, we set the maximum deviation first. The maximum deviation is, we call it gamma, okay? And this gamma is the positive value, of course, the positive number, of course. And it is the maximum deviation, okay? Where each deviation must be less than gamma. And we try to minimize this gamma, okay? We minimize gamma, okay? We have this variable of a, b, and gamma, okay? And each deviation, positive absolute value of the deviation must be less than this gamma. Okay. These are the way we formulate for the first problem and the second problem. What about the third one? The third one, of course, if you know how to formulate the first and the second one, you can do it. Okay. You just change the model. Okay. Configuration of the model to quadratic, from linear to quadratic function. Okay. Any questions? Okay, any questions? Okay, if not, we move to the next problem. The next problem we call transshipment problem. Well, the problem is, well, when we have a number of supplier, also we have number of customer, and we want to ship products, okay, ship goods from supplier to customer, okay, through the network. For example, like this, where while we have a supplier, 3 supplier, S1, S2, S3, right? And we have to ship goods to customer 1, 2, 3, 4, 5, okay, using different, well, gosh, routes. And it's possible that, well, you ship some products, some goods through different supplier. For example, S1 ship to S2 first, and then from S2 you ship to customer. Or we can ship the the product to T2 and ask T2 to ship to other customer like T1. Okay, and each route has different cost coefficient. Okay, this is the unit cost for, well, the the system show previously. And one product, if you ship one product from source S1 to S2, it costs 20. Okay, or you directly ship a unit of product from S1 to T1, it costs 132. Okay, so we're going to optimize all these shipments. Okay, we define our decision variables as S1, S2. S1, S2 is one variable, okay, not two variable. One variable, the amount of goods we ship from S1 to S2, okay? And S1, S3 means, well, the amount of goods we ship from S1 to S3. Also, S1, T1 is the amount, represent the amount of good we ship from S1 to T1, like that, okay? So we sum all possible shipment routes, okay? We also have constraint that each point, I mean, well, each variable must be greater than 0, okay, or greater than or equal 0, okay. It cannot be negative. And if we consider each node, we have a, what is it, mass balance, okay. All the shipment into that node subtract by out of that node, okay, must be equal to the amount of that node produced. Okay, for example, for S1, we ship goods out of the S1, right? This way, this way, this way, this way, this way. Okay, we have 5 possible way. Okay, and we have one shipment into S1, right? You subtract all incoming and outgoing. Okay, must be, it must equal to the produce of S1. Okay, total production of S1. Here, see. Then you consider each node. Okay, we have S1, S2, S3, right? And then we consider the customer. Okay, customer is a thing, right? It's received goods. Okay, so all the shipment coming from different node and subtract by the shipment from that node to other node. Okay, must be equal minus T1. Okay, you include all these constraints. Okay, then you can formulate the optimization problem. Okay, the next one is minimum cost flow. Well, for minimum cost flow, it's similar to transshipment problem. We have this network, okay? And at node 0 and node 1, we have incoming flux 10 units through node 0 and 15 units coming through the network through the node 1, okay? And for the output, at node 5, the outgoing, okay, it's 9, okay? The output here is 10, and the output here is 6, okay? You see that for these systems, incoming it's 25, right? The outgoing also 25, okay? So nothing left inside, okay? All we have to do is, well, how we can ship the goods through the network with minimum cost. Okay. So the decision variable we use here, we use xij. I is standing for the source, right? Okay. And j is standing for zinc. When I write x02, that means, well, the flow from 0 to node 2. Okay. So each stream come with the coefficient. Okay. Okay. Each variable must be non-negative. Well, okay. And you see that x0, 4, or 0, 2. The flow from 0 to 2 must be 10. Okay. And this flow also must be 15, right? Okay. X0, 2 must be 10. X1, 3 must be 15. Okay. Now we consider each node. Okay. For node 2, outgoing flow from node 2 subtract by incoming. Okay. To node 2 must be 0. Then you, well, consider all of these constraints. Okay. It is a mass balance at each node. Okay. Any questions? Okay, so we break for about 20 minutes. Okay, and coming back. Okay, so let us continue. So uh, now let us set up the Python and Gurobi. Previously, I told you that well, we're going to use MATLAB, right? And Gurobi and also Yamip. Then I changed my mind that well, I just realized that well, in Python become more and more popular, and and we can use Gurobi through Python. And the most important thing is Python is free to use. Okay, so what? It's just hmm? What happened to Zoom? Okay. No, I think the problem is the university network. All right. So we have okay. We're going to install Python, okay, Anaconda Python and Gurobi optimization solver. So the first thing to do is you download and install Gurobi optimizer. You go through this website, okay, and you see that well from this website, you if you are not well existing member, you register a new member, and if you have login already, well, please log in. And the most important thing is please register by using university email. Okay. If not, you will not get free license. Okay. Do it now. Okay, you can download it, right? You can, well, register it first. You already register. You doing, right? Okay, is it done? It's done already, right? Okay, so the next thing to do is, well, once you log in, you register for login, you get login, right? Then, well, once you log in, of course, welcome and your name, not my name, okay? Uh, Also here it's your email address. Download, click download, and then download Groby software, okay? The name of the software is Groby Optimizer software, okay? Then install on your system. No download option? Yeah, I will show you. Just one moment. I will log in my system. Hmm? Okay, you see, this is my screen. All right, so you click download and click Kurobi software, right? Yes, download and license. You see, there are list of available version. I don't know what your system. If you use Mac OS, you use Mac OS Universal 2. Okay, if you use Windows, of course, this is a good start for Windows, Linux, AIX, Linux. Okay, download and install by yourself. Can you do it? Can you download and can you install it? No? Oh, no, you. Ah, okay. I don't know. You're waiting for the confirmation code, right? Ah, you cannot install it. This is not your computer. Install in on your own computer. Okay. Yes. Hmm? You install it, right? Yes. Continue. And then yes. This is Mac, right? Okay. Mm, no problem. I'm using Mac too. I know how to do it. It's all right. Okay, close. Just close. Well, you can move to trash. It's all right. It's already installed. Okay. It's here. No, just one moment. No, it's somewhere. Where is this? The whole volume. I mean, no, no, it's not on the library. It's on library. Yeah, it is later. I will show you. It's okay. You install it. Hmm? Okay, for those who are using Mac, it's exactly here. Uh, one moment. Okay, it's here. You see that on the top root and in library and where is it? Yeah, here, Kurobi, Mac OS Universal 2. Okay, it's inside this. Okay, but it's okay. Then once you install, what else you need? Once you install it, you need license. Go back to the what's it? Your account? Oh no, here. Back to the Kurobi optimization website again. Okay, and then go to license here. License. Click that license. You will see a couple of things. Hmm? If I in the meeting, I don't know. What do you mean? Hmm? Can you show me your? Can you share your? Just a moment. I stop sharing. You share. You share your screen. No. Okay. If you don't share your screen, I will share my screen. Let us continue then. Okay. So once you click license, right? Click request for license. Okay. And then name user academic, this type of license. So request for license, there's button So down here, I think, yeah, down. You scroll down a little bit, you see the button here for request a license, generate now. And then, of course, you must use university network. Okay. And once you click that, if you come back on license, your license will appear here, right? The ID and also what type is free academic purpose trial or something. Yeah, I don't care if trial or not, but trial for 1 year. Later, I can request another 1 more year. And category, of course, regular. Summary, yeah, it's version 11 now. Install on. This is my machine, name of my machine. Here, you click here, license installation. Okay, and then you need this code. Grab get key. Yes, and this code. You will get different number behind this grab get key because you have different license, of course. And you have to run this. Yeah, you see, copy and paste the following command to the start run menu, Windows only. For Mac, you open terminal. You know a terminal? Ah, sorry about that. Maybe later you can try. Okay. Okay. Terminal, and then, yeah, you see, run that command. Then once you install it, and you install the license already, you can test it, run Gurobi, of course. It will show you where your Gurobi is. Okay. The next thing, you can do it. You can complete the installation of the Gurobi later. You need to install Gurobi software, and then you need to install the license. And remember that you need university email and also university network in order to generate the license. The next one is download and install Anaconda. This is quite simple because you don't need license at all. You go through this website, okay, and then free download at a very first page. Free download, okay? It's quite large. It's about 700, I think. I don't know. And the next thing, after you install Anaconda, of course, for Anaconda, you have an environment to run Python, okay? So you can run Python inside Anaconda. And the next thing to do is, I suppose that you finish installing the license, all the Groby and license, okay? And also Anaconda. Open command prompt, or in Mac, you open terminal, okay? And then this command, conda config, add channels, this channel, okay? And then conda install Gurobi, okay? It will install some file, some library, which allow you to use Gurobi inside Python, okay? You can, for this slide, well, I put this slide in my course view already. Okay, and then you open Anaconda Navigator, okay? Then, well, of course, if you love PyCharm, you can use PyCharm. But in my case, I use Jupyter. in Anaconda Navigator, click Launch Jupyter. Okay, to launch Jupyter Notebook first, and you get something like this. Okay, click Python 3 Notebook to launch the Jupyter Notebook. Okay, now it's ready. You can run the first one. It's while you can test the whether Gurobi and Python can be used in your system or not. If not, if you get something error, wow, it doesn't show like this, well, suspect that you haven't finished installing the license or Gurobi. Okay, but if you can open this Jupyter Notebook, of course, that means you finish installing the Anaconda. Okay, and the wow, for testing from Gurobi Pi import star. Okay, model is model, well, parenthesis, and model optimize, and it show something that academic license for non-commercial use only expire. Well, don't care about that. Well, or this. Okay, and now you're ready to run the first example. Okay, for the first example, I use this example. Okay, minimize 5x plus 4y subject to this the following constraint. Okay, first we use from Gurobi Pi import. Okay, we use that. We input this command in the Jupyter notebook, and then create optimization model like this. And one by one, you add these variables. Okay, the command for add this variable look like this. Model add value. For example, I declare x is a op mod, which is the name of the model, and add variable. The variable name x, and the type of variable is continuous, is real number. Okay, lower bound LB is 0. Okay, we don't have upper bound, leave it free, and declare new variable. Y is a new variable called y. Okay, continuous, and LB is, yeah, 0. Lower bound is 0. And the next thing is define the objective function. We can create this by using this command. Objective fun is 5 star x plus 4 star y. Op mode set objective. Okay, objective function graph minimize. This is type. You have two choice whether you want to minimize or maximize. Okay. And the next one is constraint. We create 3 constraints. This C1, C2, C3. Okay. Op mode add constraint, and the expression for your constraint, equality or inequality. Okay, and you can give the name to your constraint. Okay, I use C1, C2, C3 here, and then run the optimization. Okay, op mod optimize. Okay, that is, yeah, this is the result. Once I optimize it, okay, Gurobi optimizer this version, and my CPU is Apple M2. All right, I love that M2. It's quite good. That and solve into iteration, and this is the time required for solving that problem. Okay, and if well, it showed that it's solved, all right, into iteration. But if we want to see the objective function and also the optimize the result, I mean the solution, we use this command. This is to print the objective function, the objective value after optimize. And for we in op mode, get var, print the variable in the model. Okay, that is. Okay, you can try by yourself. Okay, the the first thing is finish installing Gurobi license. Okay, and then install the Anaconda. Anaconda and the link quite in in a piece of cake. But the first one, Gurobi. Okay, install Gurobi, install the license for Gurobi. Okay, any questions? I think well, people on the Zoom, you have to come back to you. Well, you have to come to university. Well, Python running. Yeah, okay. Trunk your question. The on-site is what is the room number? 306, right? This room. Yes, I know. Trunk. You
Yes.
yeah, you need the code. As I show you the code. Go back to the one moment. Let me show you again the when you install the license. And you see that grab get key. There is a wow, very long code.
Oh, yes.
Very
I
long
know.
code here. You have to copy all of this, okay, and place in the command.
Yes, I know. Thank you, Professor.
Okay. Okay, so let us let's call the day. Okay. Okay, so we finished today.